Can you hear me?
Yes.
Okay, excellent. So let's see if we can win a little bit of time. So I'm going to start, and then my PhD student, Marco, who is somewhere in the room, is going to take over and tell you a little bit more into detail what we do with deformable object manipulation. So I think that I'm going to basically just continue in the direction that Harold started, which I think was fantastic to help me then not explain all the details. Now you have all the basics. Why? Trying to get robots to do any of these things is actually difficult. And despite the fact that we do see robots interacting with physical objects and doing, well, to some extent in movies, demonstrating some of these capabilities, I would actually dare to say that doing this in open-ended environments, there are no robots today that can do any of these. Apart from that, as Harold had also said, many of these, or if not all of them, are impossible to actually get any reliable or relevant simulated data from the available simulators today. And I think we should remember this, that many of the things that we humans do without thinking actually are extremely difficult to do or demonstrate on robots. Most of the things that we do with two hands. We exchange hands, but also we are able to adapt to different media, for example. So interacting with various types of objects and materials in water, oil, and so on. And so there is just a couple of examples here, but again, these are some of the guiding lights and have been for the past 25 years in my research. So I'm going to talk about two things when it comes to physical interaction tasks. I want to talk about the need for benchmarking and also the aspect of the open source software. And I think that in the context of physical interaction tasks, what we have seen from maybe when I started as a PhD student back in late 90s to what we are seeing now is this kind of like shift of going from more analytical, classical control kind of approaches to more data-driven approaches. But the problems we are trying to solve are still the same. We are equipping robots with the capability to interact with the physical world in highly dynamic tasks, where we want to have them performing in real time, and for most of the cases actually using multi-sensory feedback. And when I talk about multi-sensory, then it's tactile/haptic, is force torque feedback potentially in the wrist of the hand. It's proprioception, so that the robot actually knows when it where you send it and it goes there. Compliance of different sort, and of course then the more range based feedback. I mean, either 3D cameras or even 2D in various types of stereo settings, laser, and so on. And I think that this is what I think we need to deal with, and why also the fact that we deal with automating complex physical interaction capabilities that have complex physical properties that go beyond shape of objects. Why are these difficult, and what do we need more of? Or what should we focus on? Is it really the open source software, or it's potentially building benchmarks and so on? Now, just to give you a couple of examples where I come from, I mean, we do like to be part of competitions. So this is one of the trainings from the Amazon Picking Challenge many years ago. So just to then think a little bit about the robot is grasping, it's grasping objects in confined spaces. I mean, the first thing we needed to do was basically to extend robot's fingers, right? Because it couldn't reach in the shelf once the object, due to maybe inexact estimation of the pose or something like that, was pushed rather than grasped. And I think that this is the first thing that comes into mind if the robot is visually servoed on the object, and the embodiment changes between the experiments. So you just extend fingers, you think. I mean, is that so easy then just to adapt in your motion planning software, or do you need to do something more extensive to really understand the reachability and so on? So I think that this just shows that even the small changes in the embodiment are not always easy easy then, even if you have access to the open source software, just digging into, okay, where do I put that number of extending the fingers, or do I need to rechange completely the way the motion is planned? So this is what I would say. Is it better to write it from the beginning, or really take and adapt somebody's software if it's not well documented and so on? Now, when it comes to other types of tasks, like the physical interaction with human, again, here, there are many, many challenges, which also we don't have, I would say, good ways of sharing the software. So what is important here? Do we all use the forced-torque feedback and have this kind of like compliant control task solved? Does the robot or the software really understand where the limits of the joint limits are? Does it appropriately address when the robot comes to a as I said, either the joint limit or whether the Jacobian works well and so on? My point is that any of these tasks that need to be done in interaction with a human need to be safe from the beginning. So how do we, just by taking somebody else's code, can also rely that the for this type of tasks, the software is really safe? How do we ensure that? So again, I think that it's good with having the open source software, but when it comes to direct physical interaction with a human, it's extremely important to bear that in mind. Other types of interaction tasks may not involve humans, but they may involve something like this, interaction with physically varying objects. So cutting through a raw potato or cooked potato or a banana or a squash and so on. Let's say that the idea here is to basically study development of either classical control-based approaches, analytical, or something like data-driven and so on. How do we ensure that during the task, the robot, based on then the force torque feedback that it gets, it does not generate so big torque so that the robot breaks? Now, when it comes to ABB UMI, here you will have something like limits in the joints by design, but not all the robots have that. So we had examples where the robot was just basically applying more and more force. And again, having humans close to robots is definitely not something you want to have. But more importantly, I mean, how many robots can we break? And none of this can actually be simulated and then studied in simulation. So just kind of like thinking, again, how do we put that safety, how do we have a safety framework around something that we then release as open source? Another type of human interaction task, and this is also something that Harold has said about, is about observing something that the human is doing, potentially being or using the dialogue, instructing the robot what the human needs help with. But the vision for the future is really to actually have the robot as a third hand, right? So robot observing the human, and then from visual feedback, because what else, right? It needs to understand how to instruct the human whether more flour is needed in the dough, right? So it would look something into something like viscosity of the dough, or it would potentially look into how much of the dough is on the human fingers and so on. And I think that this just tells us how this kind of the embodiment or the physical aspect of what the robot is seeing and the contextual knowledge can actually not be easily programmed in these large language models just as yet. So I think that from the robotics and HRI point of view, what we really need to come up are these demonstration scenarios, right? That can just show, well, if the robot doesn't understand the viscosity, because the viscosity is not something you get as a number, right? Maybe it has it as a number, but it then needs to ground it in what it sees and understanding what it should look for. So I'm really looking forward in having like GPT-3 or whatever, 33 or something like that, looking into what will be the dialogue or the instructions that need to be given to the system so that the system can really understand what to actually look for. And I think that that also, again, relates to both building the relevant benchmarks and then providing the relevant open source software for being able to actually extract some of these relevant information, such as, for example, being able to track human fingers, being able to track deformable objects, and so on. Now, again, having human in the loop and having direct physical interaction with a robot, it's extremely difficult to understand also how the human experiences many of these tasks. So in our studies, we look very much into how we can use non-invasive devices such as EEG to understand in various types of either collaborative tasks, playing tasks, and so on, what is the human's entrainment time, and also whether, dependent on what the goal of the task is, whether the human gets frustrated or for how long the human can actually do something physically with the robot without being irritated, as I said, frustrated, and so on. And I think that, yes, we can do lots of user studies and ask them how they felt and when they felt it, but it would be really, really nice if they can engage directly in these physical tasks. And then while they are being engaged, we also measure some of these properties. So that would be also rather interesting to see how would both the scenarios and then what would be shared here also from the perspective of some of these data maybe not being so easily shareable due to ethical aspects of the experiments and so on. But again, we are seeing a trend of more people being interested in integrating this kind of like more neuroscientific or cognitive science experiments together with various types of control algorithms used on robots. Now, I want to move a little bit on what Marco is going to talk about, and this is how we can also build various types of environments for studying physical interaction with deformable objects, such as, for example, clothing items. And it might be for the purpose of recycling these or just assessing their quality or potentially assistive dressing. And this is just one example that shows you, how difficult it is, even if you pre-program lots of parts here for a dual arm system to pick up an item, plan a set of actions or movements of this dual arm setup to actually make or bring the sweater or the t-shirt in this case in a pose or a position or a state from which it can be dragged over what is to represent the human head, so the green thing. And I think that is it relevant to build something that people can try and test, and from what perspective? Is it in terms of the coordination of the arms, from the perspective of task planning / motion planning? Is it from the perspective of potentially using various types of Bayesian optimization algorithms to kind of like deal with the techniques for adapting, for how to safely, to some extent, move the item across somebody's head, arm, and so on. And we work mostly on looking and trying to understand what is to be benchmarked and assessed or built before we understand the complexity of these, and how we can then also provide the software so that, again, if somebody runs the software on their dual arm setup, which maybe has a completely different kinematics, and the elbows are on the side, not bolted on the table surface, and so on, to make sure that the robots don't collide with the table, and so on. So there are many things one needs to think about when then making what we say then the open source software safe. Now, I love tactile feedback, but just to show you again what is difficult. So maybe at some point we will have robots that can do dishes or wash dishes. I think that this is fantastic how humans are using their two hands, but also some high level knowledge in terms of what you manipulate in order to be able to control both the velocity and acceleration and the forces applied and so on. And I think that this is something that, again, we can talk what we do, but we can't put numbers. So I use 5 newtons on a porcelain ball, and I'm using 10 newtons on something that is made out of wood. It just doesn't come natural to us. We can't even explain what it means that something is slipping or how does that feel, because we just know it in a way, or our brain knows, and so on. So yes, we can equip robots with all these rather expensive sensors. We can do what we have demonstrated many years ago, finger gating. We can regrasp things. We can deal with external disturbances and so on. The problem is that even if we release lots of this software, the problem is that the numbers, or how the sensors, in particular, the syntax, needs to be recalibrated after maybe 10 or 15 times being used, right? So you actually need to take a syringe and fill the fluid into these sensors, because the vibrations that you measure basically change. And I think that this is interesting, right? That not many people think of this, that in the experiments, if you actually apply lots of these disturbances or change the state, it actually affects the readings of the sensors. And I think that yeah, we have heard that thinking of the design, how do we design them for this rather difficult tasks, is extremely important. But we do talk a lot about in-hand manipulation, although not it's not so easy to demonstrate. So one of the things that again I will end up with, and Marco will take over, is about how do we then build environments that are relevant for asking questions that have to maybe do with deformable objects or planning motions on deformable objects. So this is one of the recent NeurIPS papers that we did for building environments with what we call topologically non-trivial deformable objects. And it was in the middle of COVID. So we looked into we were very inspired by putting masks on our faces. So we'll look into how we can build still rather realistic environments, so that we can study these independent of the embodiments, and to some extent also independent of the feedback. So I'm going to stop here. I'm going to stay until the end for questions, and then Marco, if you can take over in 3 seconds.
So yes, I'm going to continue on the presentation on Dani, talking about how we can use interactions, in this case with in-protein manipulation, to address challenges that arise when manipulating protein items, as well as how we can improve the interfaces that are currently used for the collection of these interactions, using also the human in the loop. So it doesn't.
I might just need to click.
Okay. So first of all, it's important to start to understand why these objects are more challenging to manipulate than normal rigid objects. First of all, they have an infinite number of degrees of freedom, and this makes their configuration space to be as well infinite dimensional. So it's more challenging for the robot to plan the sequence of motion, the sequence of actions that it has to do in order to perform the downstream task. But also these objects present a large variety of different properties, which are influenced, for example, by the different material or construction techniques of clothes. And this, of course, makes it more challenging for the robot to adapt the manipulation strategies to these different properties, as well as makes it more difficult to actually model the dynamics of these deformations, and having models that can be computationally not too expensive to model these deformations. And these challenges arises in most of the tasks that robots are used in current research. For example, in different ways, in different tasks. For example, in the folding and flattening tasks, the fact of having an infinite dimensional configuration space may be more relevant. while in an assisted dressing scenario, taking also inspiration from what Taco was presenting this morning, if we have to dress a person with a pair of pants which is made of jeans, the strategy might be very different than from dressing a person with, for example, a pair of leggings, so more elastic material. But in this case, to address these challenges, interaction data can be helpful. And one project that we recently accepted to ICRA in this direction was to try to generalize a model to different elastic properties. Where in this case, we used pooling interaction to extract, collected from a lot of different samples, 40 different elastic samples. And we used an encoder to encode these elastic properties with the goal then to transfer this information in a new downstream task, which in this case was exemplified by this partial bandaging on a human heart, so two possible assisted dressing scenarios. And to do that, we also taken from what Dani said, we used a combination of different sensory input. In this case, we used observation as graphs collected from images, as well as coupling this with force information perceived at the end effector of the robot. So this gave us the information to obtain a later representations of these elastic properties that then can be transferred to a new task, a new downstream task. And instead, in another setting, in this case, cloth folding, we can still use interaction to tackle the challenge of having this infinite dimensional configuration space. Here, the problem is formulated as from a starting configuration of our deformable object, shirt in this case, we want to arrive to a goal configuration. So in this case, we want our robot to provide us with the series of action and states that the robot has to achieve in order to arrive to this goal configuration. But of course, being this space infinite dimension, it's very difficult to plan this motion. But using the action information, the interaction information in this case, and know when an action has occurred or not, we know when two different states are different because an action has occurred, or when they are the same because no action has occurred, so we can cluster them together. And by having this, doing this over a data set of interaction, we can have the same states clustered together in latent space, while different states clustered further apart and connected by an edge. And in this case, we can obtain this graph, which allow us to plan the sequence of motions in order to achieve the goal configuration of the folded state. So both of these are examples of works in which interaction can be useful to address challenges with floating items, but of course there are a lot of different tasks which can also use a different type of interaction in order to improve the performance. But given the variety of these of properties of these floating items, of course, this becomes a very expensive process. Since also these models are usually very data hungry. And so this motivates also a new direction that I'm taking, which is to improve this data collection process and make it more intuitive for the human and less expensive in terms of effort, by building a virtual reality environment in which the human and the robot can collaborate in order to obtain interaction data. So in this case, this framework is composed first of a representation extraction part, in which basically the framework provides a sequence of pick and place points that the user can modify according to which parts of the cloth it wants to be manipulated. And instead, a second part in which a robot can propose a type of folding action, for example, saved from a previous interaction, and the user can modify both the type of nodes that the pick and place nodes, as well as possibly the trajectory for the robot, because the outcome might be different according to how high the robot moves the floating item. And that's it for presentation. So if you want to ask any question, feel free. Questions?
I'll ask you a question. So for your deformable object manipulation, like when you're doing planning in latent spaces, how do you know that you have generated a good latent space? The reason I'm asking is like for deformable, like it's a very high dimensional state,
Yes.
right? And I'm just wondering, is it possible that if you plan in latent space, you might lose out on some information?
So, I mean, definitely, like the information is all contained in the dataset in this case. So, of course, there are states which might be out of distribution, some particular configuration of the shirt of the clothing items which cannot be reached in this case because, of course, the action is not present. The robot will know the action to perform in that case. But with a lot of effort, of course, you can collect a lot of data and try to cover all of these blank spots in the data space. And that's also why we are trying to get new ways of making it more automated to the process of data collection. Or as well, you can consider to have some strategies that allow you to understand which is the closest configuration in the latent space to the one that the robot is observing, and then try to have a similar action to that. But that's not part of what is currently in the model itself. Any other question?
So on the question of open source, so there's data sets that you all have generated, right? That I assume can be contributed to open source, but
Yes.
to, I think Harold had to run off to pioneers. So to Harold's question earlier about like, is generating the data set enough, right? He talked about kind of all the endeavors of trying to integrate it and use it and everything. I'm curious about kind of your Danica's thoughts on how the data sets you've generated could be utilized by other researchers. Would you imagine they'd have similar obstacles that he faced, or have you done anything to maybe try to rectify any of those issues?
So what I can, yeah. So one thing is really understanding what you can do with the methodology, right? So we have generated both the software and then the benchmarks where we could show that encoding things, you know, with variational autoencoders or something like that can be equally used for maybe folding clothing or for stacking objects. So that's one thing, kind of like scientifically, just trying to understand the methodology, right? But then the second is much more related to the physical embodiment of the robot. And I think that that's another thing, right? Explaining well how the action was encoded and connected to then the latent space representation. And so what in the whole system, because there are so many steps, right? What is that we can kind of like do with our, you know, dual arm Franca setup. But now if you want to use that on Baxter, or if you want to use that if the PR2 is still working and so on, I mean, it will be very likely then either build on some ROS node or something like that, or using movie, I mean, you know, as it was mentioned. So I think what is important is that we communicate well what actually can be also transferred between different embodiments and what needs to be done. But is it enough? I don't think so, because what we are also seeing, and I think that that has to do with question number one, right? Just understanding what are the error modes in a way, and those will be shown, you know, very soon if you just take a little bit different t-shirt, if the sleeves are not equally long and so on. And that has to do with a variety or generalization properties of then how the perception algorithms are, or how the representation is really learned on the perceptual data. And I think that in itself is a big question. Can we, for any of these robotics tasks, really consider action without perception or perception without action? Does it make sense, right? Does it make sense to really kind of talk about providing these algorithms that students spend lots of time on trying to understand and trying to adapt, or just starting something from scratch because you really wrote your ICRA or IROS or RSS paper well, so that it's easy to understand what you actually did. And my understanding is that no, I mean, we need to, in a way, do both, right? But I still think that we have a little bit of a difficulty of writing papers. So revealing in the paper what is reproducible and what's not. Yeah, so maybe that's where we should start. Really writing papers so that everything that we have done can be easily reproduced, not only just providing the code. I don't think that that's, you can have good code and bad code.
I like the comment about what is reproducible and what isn't, because I think that sufficiently limiting someone's understanding of replication is just as important as making it replicable, because there may only be some pieces of it that are actually replicable. Or Ross had a comment earlier about the differences between systems and this many linkages, this many that. What are those baseline parameters you need to have in order to even to have a chance? All right, any other questions? All right, thank you very much.
Thank you.
All right.